In this lesson, we'll analyze graphs of rational functions and see some applications of rational functions. What is a rational function? Well, as you recall, it's a fractional expression such that the numerator and denominator are polynomials. So any function of the type p over q, where p and q are polynomials, and obviously q of x has to be different than 0 because we can't divide by 0, is a rational function. Since rational functions involve division by something, we really have to be careful and every single time check if we are not dividing by 0. So the domain of a rational function consists of all real numbers except for those that will make denominator q of x equal to 0. Therefore, we can write the domain of function f is all real numbers except for the set of points that will make denominator 0. And here we have some examples of various rational functions, how the graphs of such functions may look like. Well, they usually consist of few branches, either 2 or even more, and also you may expect some asymptotes, that means lines that the graph is approaching, but usually don't touch them. So for example, in the first graph, we have one vertical asymptote coming through -1/2 and one horizontal asymptote coming through 2. We can also relate this graph to the equation of it, because if we solve the denominator for 0, the x will happen to be exactly -1/2. So that must be connected with the denominator. Now the horizontal asymptote that comes through 2, the 2 comes from actually dividing the leading coefficients. So in this case, it's 4 divided by 2 is 2. That's why the horizontal asymptote is actually at the level 2. I placed the second graph here just for your enjoyment. We see a little bug here that is sliding on the curve on our function. Well, whenever the function behaves in that way that the little bug can actually slide down, then we are saying that the function is decreasing in this region. And over there, the bug will actually have to climb up. So those are the increasing sections of the graph. Notice that we always assume that the bug is proceeding from the left to the right, never backwards. So on her trip from the left to the right, the bug is either climbing, that's the increasing part, or sliding down, that's the decreasing part. And another example of a rational function. This is a little bit different than previous ones because we also have a slant asymptote, not only vertical ones, but also a slant asymptote. That may happen. Well, let's analyze a graph of this particular rational function, x plus 1 over x minus 2. What is the domain of function g? Well, as we remember the definition, the domain will be all real numbers except for those that will make denominator 0. So the domain of the function g is all real numbers, but not which number makes it 0? 2, so except for 2. We also have the graph of this function given. You are always welcome to plug it in the expression to the calculator and see by yourself that that will be the graph of the function. Notice that the number 2 is here, and that's the place when the function doesn't assume any value. This is the point that does not belong to the domain. So domain is everything else except for 2. The second task is finding x and y intercepts. So how do we find x-intercept? Well, to find x-intercept, we set y equals 0, which means the g of x is 0, and we're trying to solve equation x plus 1 over x minus 2 when this equals to 0. Obviously, a fraction is 0 when the numerator is 0. It does not depend on the denominator at all. So this is 0 when x is equal -1. Therefore, x -1 is our x-intercept. And yes, we see -1 to be here, and the graph crosses this point. Now to find y-intercept, we set x equals 0, meaning we really evaluate g of 0. So plug it in 0 instead of x, we end up with negative 1/2. So y-intercept is negative 1/2. Let's see on the diagram. Oh, that looks like this point, negative 1/2. Yes, indeed. Now let's observe the behavior of our function g, that's g function, for x values approaching 2 from the right. So 2 is our point out of the domain, but we're interested in what's going on with the values of the function when x is closer and closer to 2, but from the right-hand side. That means by numbers that are a tiny bit larger than 2, but they are very close to 2. So coming from the right-hand side, what's going on with the values of the function? Well, they run away towards infinity. Therefore, we can record this fact. If x approaches, just use the arrow to indicate that something approaches, x is going towards, x approaches 2 from the right, we use a little plus at the top of the number 2. So we read this: if x approaches 2 from the right, then g of x, which is the value of the function, approaches. And what does it approach? Well, it's going this way. It's going towards infinity. It approaches infinity. Similarly, if x approaches 2 from the left, if x approaches 2 from the left, negative side, that means by numbers tiny bit smaller than 2, what are the values of the function? Well, they are going towards negative infinity. So then g of x is approaching negative infinity. That's how we describe behavior of the function around point 2. So these two statements really catch the property of asymptote. From the left-hand side, the graph is trying to approach the asymptote by following this line towards negative infinity, and from the right-hand side towards positive infinity. Observe the behavior of g for x values approaching infinity. Well, now we are running with x's towards the infinity, this way, and we're observing what's going on with the values of the function. Well, those values of the function are trying to approach the horizontal asymptote, which comes through the point 1. So, using the diagram, I would say the values approach 1. Similarly as before, if x approaches infinity, then g of x approaches 1, but by numbers tiny bit larger than 1, so we can say approaches 1 from the positive side. We can be a little bit more precise here. And finally, observe the behavior of g for x values approaching negative infinity. So this time we're looking what's going on when x's are running towards negative infinity. What's going on with the values of the function? Well, those values looks like they are closer and closer to 1, but by using numbers that are a tiny bit smaller than 1. So let's record this. If x approaches negative infinity, then g of x approaches 1 from the negative side. So that's really introduction to limits that will be quite useful for those who go into calculus course. So we built some intuition about asymptotes. Now let's define an asymptote. For example, what is a vertical asymptote? Well, if we have a function f of x that approaches either positive or negative infinity, as x approaches certain point a, either from the right or from the left, plus or minus, then the graph of f has a vertical asymptote, and this vertical asymptote has equation x equals this particular a. So we may have a situation like on this first diagram, when x approaches a from the positive side, that means x's are closer and closer to a from the right, then the values of the function are really running away towards infinity. That means that we have a vertical asymptote x equals a. Remember that asymptote is a line, so it has its own equation, but this line is not a part of the graph. In the second example, we have similar situation, but this time x approach a from the left, and again the values of the function are running away towards infinity. That's why we have a vertical asymptote at the point a. Third graph represents the situation when x approaches a from the positive side and the graph is running towards negative infinity. And the next one, the x's approach a from the left and the graph is running towards negative infinity as well. So those are the four possible cases when you get vertical asymptote. The graph doesn't necessarily have to run to the infinity from both sides. It's enough to run only from one side and we still have an asymptote. Now, how to find a vertical asymptote when you have a rational function? Notice that vertical asymptotes will occur at those points that are not in domain. So if we have a rational function p over q, and p and q have no common factors, that's quite important. All common factors are reduced, and if we have an irrational number a that is a zero of denominator, then the function f has a vertical asymptote x equals a. Okay, so knowing this fact, let's practice a little bit. Find the equations of all vertical asymptotes of the given function. Then using graphing calculator, show the approximate graph of the function. And we have two examples. Well, in order to find equations of vertical asymptotes, I need to factor the denominator, reduce if possible, and if the numerator and denominator are relatively prime, there is no more reduction, then check when the denominator is zero, and those will be the points that will create vertical asymptotes. That means not all points from the domain. We can't at once assume that every single point that is not in domain of the function creates a vertical asymptote. Sometimes they may be holes, and we'll see this in a second. So the denominator factors into x minus 3 and x minus 2. Well, notice that x minus 3 can be reduced with the numerator. So if we reduce this, the expression becomes 1 over x minus 2. I'm not saying that this is the same function as the original f of x. However, it's useful to graph f of x. We know that 2 is out of the domain, so let's mark the 2 here. And since this expression is already simplified, the 2 will produce a vertical asymptote like this. So we can already claim the equation of vertical asymptote is x equals 2. That's our vertical asymptote. Okay, but someone can say, what about the domain of f? Well, the domain of f is all real numbers minus the two numbers from denominator that will make them 0, which means not only 2 but also 3. So minus 2 and 3. Well, we already discussed number 2. However, what's going on with number 3? Maybe at this moment, please stop the video and plug it in the expression, either this one or that one, to the graphing calculator and see the shape so we can graph it. Here I introduce the first function x minus 3 over x squared minus 5x plus 6, and let's see the graph in the window from negative 5 to 5 on x-axis and negative 5 to 5 on the y-axis. So the graph looks like this. Okay, using the graphing calculator, we observe that we have another asymptote, that's horizontal asymptote, which is the same as x-axis, and the graph of this function looks somehow like this. It has two branches. We're quite used to this shape. So, what's going on with number 3? Number 3 is somewhere here. Well, the number 3 doesn't produce the vertical asymptote. However, it does produce a hole a hole in a graph because the tree is not in domain, so we can't really evaluate this function at 3. There is no value at 3, it's empty point. So the graph follows the regular shape of 1 over x minus 2, but we have to remember to kick out this one single point. And that's how this expression differs from that expression, just by different domains. This is domain of f. However, domain of this expression would be just r minus a single point 2. So formally they are not equivalent, they are not the same. They would be equivalent only in a common domain, in the domain that works for both of them. That means in this one. Okay, let's see the second example. Here if we factor the denominator, we have x times, and then it's x squared minus 4x plus 4. You can observe that this is a perfect square of x minus 2 squared. Since we can't really reduce anything, therefore each factor from the denominator gives us a number when the graph of g has a vertical asymptote. So all equations of vertical asymptotes for this graph are as follows: x equals 0 because of this x, and x equals 2 from the second bracket. So let's graph these two asymptotes. X equals 0, it's a y-axis, and x equals 2 somewhere here. That's 2. And again, let's plug it in this formula to the graphing calculator, see how the shape looks like, and see if you can guess a horizontal asymptote. That would be x squared plus 1 divided by x cubed minus 4x squared plus 4x. Make sure that you use brackets around the numerator and denominator. So let's graph it. It looks like we have 3 branches. So it happens that this function has a horizontal asymptote also at 0. It is x-axis. And the shape of the graph looks somehow like this. And here, somehow like that. Notice that the asymptote at 2 attracts the graph from both sides. Both sides of the graph goes towards the infinity. Well, that could be contributed to the fact that number 2 is a root of denominator of multiplicity 2. So we end up with kind of even situation from both sides. Well, let's summarize what we observed. If a is a 0 of multiplicity n of the denominator of our rational function, then the graph of rational function with this denominator around a looks as follows. If n is odd, for example 1, 3, 5, then the graph approaches this vertical asymptote at a in different ways, from the left to the minus infinity, from the right to the plus infinity, or otherwise, but they're going apart to different infinities on both sides. However, if n is even, then the graph tends to go towards the same side, so either both to plus infinity or both to negative infinity. Okay, so we know quite a lot about vertical asymptotes. What about horizontal asymptotes? So far we've been just guessing our equations of horizontal asymptotes by looking at the graph on the graphing calculator. But here's the formal definition. If a function f approaches certain number b as x approaches infinity or negative infinity, what does this mean? That means that if we go far away towards infinity or far away towards negative infinity, the function tries to stabilize. They try to approach the same constant value. Let's call it value b. Then we can say that the graph of f has a horizontal asymptote y equals b. So here are the possible situations how we can see the horizontal asymptote. The graph may approach to it from the bottom, it may approach to it from the top, it may go across the horizontal asymptote and approach either from the bottom or from the top. Could be like this, could be even way more often and finally stabilize somewhere. That's okay, as long as for large enough x's the graph is very, very close to the asymptote. So horizontal asymptote can be crossed by a graph, while vertical asymptote will never be crossed because vertical asymptotes occur at those points that are not in domain, so there's no value for a function. However, horizontal is okay to cross as long as the graph sooner or later is approaching this particular line. And the third type of asymptotes is called slant asymptote. If we go far away with axis to the positive or negative infinity, and we observe that the shape of function is approaching certain line with the equation mx plus b, for example, on this picture the line is 2x plus 3, and the graph is trying to get closer and closer to this line here and there, very, very close, right? So as long as we have this situation, then such a line is called slant asymptote. It is slant because it's neither horizontal nor vertical, it's just some other line. Here we have a very important theorem that I really wish that you will get familiar with because it helps you to find out asymptotes and recognize the shape of the function very quickly. So that theorem is about horizontal or slant asymptotes. The slant refers to a linear asymptote, but we can also think about curved asymptotes. The graph of the function may actually approach, for example, x squared or some other curve, not necessarily a line. But most often we'll be just interested in slant asymptotes. So let f of x be any rational function, which means that it can be expressed in that form: some polynomial of nth degree in the numerator and some polynomial of mth degree in the denominator. Now the leading coefficient must be non-zero because otherwise the degree of the polynomial would be different. Then the graph of a function f has a horizontal asymptote y equals 0 if the denominator is of higher degree than the numerator. That means we have something bigger here, something bigger as a matter of exponent. So m is larger than n, then we have a horizontal asymptote just in the x-axis. If m is equal to n, that means these two polynomials are of the same degrees, then we still have a horizontal asymptote, but its equation is actually y equals an over bm. That means we're taking leading coefficients to determine how high is positioned the horizontal asymptote. And the third type of asymptote, slant or curved asymptote, occurs when the degree of the denominator is actually lower than the degree of the numerator. But think about it. If the degree of the denominator is lower, for example, in the denominator I have x, in the numerator I have x squared plus 1, then we can actually divide by x. So that's exactly what we do. We take the slant asymptote as a quotient from the division of the numerator polynomial by the denominator polynomial. So we divide those polynomials and we're taking only quotient. We don't worry about the remainder, just the quotient. That's your slant or curved asymptote. It will be slant if the quotient is a linear polynomial. That means if the degree of the numerator differs just by 1 from the degree of the denominator. Okay, so those are the rules, quite important rules to remember. Let's apply those rules and find equations of either horizontal or slant asymptotes for the given function. Notice that if a function has a horizontal asymptote, that means the degree of the denominator is either bigger or equal than the degree of the numerator, then it can't have a slant asymptote because then we would have to have the degree of the denominator lower than the degree of the numerator. So it's either a horizontal or a slant asymptote if we deal with rational functions. Okay, let's see what kind of asymptotes we'll have here. First, think about the degree of the numerator and denominator. Since it is the same, we are in the second case. So the equation of a horizontal asymptote is y equals the quotient of leading coefficients. So it's 2 over 1, therefore it's just 2. Oh, that's great. We have a horizontal asymptote 2. We can plot it, y equals 2. The graph must approach this line in a long run. What about vertical asymptotes? We already know how to find vertical asymptotes. Those are created by points that will make denominator 0. However, this particular denominator will never be 0 because you have something to the 4 which is always positive plus 1, so it's definitely bigger than 0. So there is no vertical asymptotes. We have only one horizontal asymptote. Okay, at this point, let's go through all three functions, figure out all the asymptotes first, and leave the graph for later. After we'll have all asymptotes, I will ask you to stop the video, plug it in all expressions to the calculator and graph by yourself, and then start the video and confirm with my graphs. So, second case, g function. What do we know about the degrees of polynomials? The numerator is larger than the denominator, is larger exactly by 1. So in order to find out asymptote, we need to go through long division. Okay, maybe on this side, we need to divide x squared plus 0x. Remember to replace missing term by 0 minus 9. Divide by 2x minus 4. So 2x goes into x squared, 1/2 x times. Okay, if we multiply, we'll have x squared minus 2x. Then we subtract, and we end up with 2x minus 9. Drop the next term. Now 2x goes into 2x exactly one time, and that's all what we need because the next part will be already remainder. So we don't need to proceed any further. This is already our equation of the asymptote. So this asymptote is really called a slant asymptote. And the equation of this asymptote is y equals 1/2 x plus 1. Okay, we're ready to graph. Starting from 1, slope 1/2, so 2 across 1 up. That's the line. The graph must approach this line in the long run. What about vertical asymptotes? Well, we do have 1 because 2x minus 4 is 0 when x is equal to 2. So the vertical asymptote is when x equals 2. Let's graph this one. X equals 2 is here. Okay, so our graph will be navigated by these two lines. And the third example, well, now the denominator is heavier than the numerator, so we know at once that we have a horizontal asymptote of the type y equals 0. That's the first case. So let's graph it. Y equals 0. And to find the vertical asymptote, what we need to do is actually factor denominator. That will be x minus 3 and x plus 2. So we have 2 points out of the domain that will produce vertical asymptotes. So those vertical asymptotes will be x equals 3 and x equals negative 2. So again, let's graph them. X equals 3 somewhere here, and x equals negative 2 over there. Okay, so we have some sort of vision how the graph. The rest of it needs to be checked by checking some points, by analyzing the behavior around the asymptotes. But for now, we'll just use graphing calculator. And please do it on your own, and in a second just confirm if your graph looks the same as mine. So the graph of the first example looks somehow like this. The graph of the second one looks somehow like that. And the graph of the third one looks somehow like this. So my graphs may not be perfect up to each point, but they are a good approximation and they catch the main properties. So that's all what we need.